appear, and I'll join you later again.
All right. Thank you very much, Luca. Thanks for having me. Today, we'll be talking about the intricacies of managing data platforms and merging that with, let's say, Kubernetes deployments, and how to actually do away with all of that, let's say, baggage of data engineering platforms that have emerged over the last 2 decades. Specifically looking at the case of Spark. So without much further ado, I'll start my presentation. So just a quick intro of myself. My name is Erik Schmiegelow. I am CEO at Hivemind, and we're a data engineering company and based in Berlin, Germany. And we will be talking about finally saying goodbye to Hadoop and saying hello to Kubernetes. To understand that also specifically, we'll just delve into the intricacies of Spark as a main data engineering platform. And we'll then look at the deployment and runtimes of Spark later on. Before we actually start, it would be a good thing to maybe get a recap and a bit of a check-in of where we're actually coming from. And specifically also understanding what data platforms and data engineering actually means and how that differentiates from, let's say, the normal platform engineering and application runtimes that we see today. And in order to do that, we have to go back a bit in time, notably to, like, let's say, the first half of the first decade of this century. So that's how old all of this is, and basically look at the inception. And that happened specifically when Google published a few white papers. And those white papers were really, really interesting and electrifying for our industry, because they also very, very well described how Google actually solves data problems at scale. 2 of them were basically MapReduce and the GFS. These 2 specifically described how to store data using cheap hardware with high fault tolerance and high redundancy, and described the framework to process data at scale equally using cheap boxes. And the importance of this is specifically because it also allowed for the very first time to do massive scale out of data processing on very, very cheap hardware, basically for the rest of us, as opposed to, let's say, the traditional way of spending millions of dollars in very, very expensive machines, supercomputers and mainframes and the like. So for the very first time, we had a concept of distributed computing and replication in an affordable way. And on top of that, it also had a really, really simple computing model. So it was very, very simple for people to adopt that. And the first big users were obviously the ones that needed that most, for instance, Facebook and Yahoo, with enormous installs, right? With thousands, tens of thousands of nodes by 2011. But despite the simplicity of the computing model MapReduce, it actually really sucked, because it was predominantly one thing. It was an algorithm or a computing model that allowed us just map some data and to send it to reduce jobs, and that's it. So essentially, if you wanted to do anything more complex, you needed to chain a lot of those MapReduce stages to one another, creating enormous stages of multiple jobs running one after the other to do basic computation. And the major drawback is that you basically try to press any kind of, let's say, job chain into that simple model, which meant that pretty much quickly, new frameworks and new approaches emerged to improve on that and have, let's say, a more flow-oriented computational model, rather than having the simple, constant repetition of the same simple steps. But that was also not really enough. And by 2009, the folks at Berkeley said, okay, we need to have something that is actually more reliable and also more abstract. And in came basically the Spark project that allowed the ability to describe jobs and computation tasks in directed acyclical graphs of computational changes that or basically in consecutive order. And what they also did was they wanted to create that abstraction model to allow, let's say, less engineering focused and more scientific users to use these platforms. Hence also creating high-level APIs for different languages other than the native Scala language of Spark. So basically having bindings for people using Java, Python, or R. The later two specifically curating to the data science community, allowing a more easy access to that raw distributed computational power that basically distributed computing on top of Hadoop actually allowed. And Spark was also designed in such a way that not only ran on Hadoop, which was is probably the most to date the most popular installation and cluster mode, but also basically its own infrastructure and others, notably Kubernetes. The cool thing about Spark is that it also allowed data scientists and data engineers to do quite a few clever things with the platform, notably machine learning, graph computation, also stream processing, and also just basic analytical jobs using like a SQL similar language called Spark SQL. And the reason why they did that was predominantly to offer an entire tool set to those departments that really needed that power most, specifically business intelligence, data warehouses, and also predictive units that needed machine learning capabilities on top of their platform. What Spark also really did very well was allow plugging different data sources into one main platform, hence also its great popularity. It allowed us to basically plug into different sources such as Google Buckets or S3 HDFS with different formats, also operate on streams such as queuing systems, Kafka, even Twitter feeds, and write things back to different stores such as Elasticsearch, Cassandra, or just plain relational databases, which also meant that we were slowly, with the Spark is slowly also gaining traction in areas that are more native to, let's say, standard enterprise computing and application development areas rather than the classic data warehousing and business intelligence systems, which presents, when we think about platform engineering, with unique challenges because it becomes more frequent and more challenging to operate these types of application and data platforms running on Spark in the context of platforms run by operators. Thinking of Spark specifically in the context of microservices, if you want to basically have a basic understanding of what Spark actually does and how it differentiates from microservices, it's more like a freight train, right? So it is a framework that allows us to process large amounts of data, carry them, albeit slowly, but very effectively from A to B. Whilst microservices are more like, let's say, slick, high-speed trains with one purpose, and they do very well and quickly. So generally, also when we think about runtime behaviors, Spark's jobs are slow, they'll carry a lot of data, whilst traditional microservices are fast, but can't carry that much payload, right? How does that actually specifically work, right? And also differentiate from microservices? Well, it's because Spark is not only just an environment to write jobs that process a lot of data, it also comes with a very clever mechanism to scale up and scale down its workload according to the amounts of data that it has to process. It also differentiates itself from traditional microservice frameworks that we use in different containers, because it basically has that ability to plan and dynamically allocate resources in for its specific job. And the way it does that is it creates this job that runs, creates a context that does basic planning of execution and division of labor of those jobs. And it relies heavily on the cluster management of the underlying cluster technology to basically provide resources to it. That's actually quite unique compared to, let's say, traditional frameworks that we use in microservice land, because it basically does all of that coordination pretty much automatically and dynamically. And that is essentially one major differentiation factor, specifically because Spark as a framework looks at what the job looks like, how it's structured, and dissects that into separate units and steps, right? It says, okay, this job will just take this amount of data, map it to that, and then it's going to do some accumulation, and then a third step and a fourth step. It basically dissects all those little steps into different execution stages, and each time a stage gets started, it will then ask the cluster manager to say, well, I'm going to need these boxes, I'm going to need these resources in order to run that job. Please provide provide some instances, and I'm going to run my execution on a worker node, on an executor, as they're called in Spark, and I'm going to run that task there. The clever thing about Spark is it also has the ability to, let's say, observe the outcome and restart a task if necessary. So there's a lot of, let's say, automation that makes it very effective to use for large data sets, because you can rely on the job basically being planned adequately, scaled adequately, obviously provided that the cluster can provide these resources and the jobs are configured in a certain way to accommodate the amounts of data that we want to process, but it's actually quite clever in doing that. So at the end of a job, you have quite a number of stages that represent all the different processing steps required to execute the job. In that sense, it's also much more clever than the old MapReduce paradigm, which required that be planned and coded manually by the engineers writing the job. So in a nutshell, Spark is actually quite clever because it removes a lot of the boilerplate around distribution and data sourcing. So you can basically say, okay, I'm just going to plug into that source. I'm going to the Spark automatically detects formats and creates a schema for that. You can do your transformation. It basically allows a very simple computational level of data structures, and will basically plan those jobs and run them for you on the cluster, and is therefore also massively superior to what it used to be in MapReduce. That also is the reason why Spark is so popular in data engineering. So if we look at the runtime behavior and the runtimes of Spark, how that actually maps nowadays, we basically immediately bump into Spark on Hadoop, because let's say 60% of the deployments run on Spark, on Hadoop, of Spark run on Hadoop. And most of these deployments run on cloud infrastructures. So you basically, in each of the public clouds has their own Hadoop distribution that can run Spark, be it EMR on AWS or Dataproc and GCP HDN sites. And that basically tries to encapsulate the pain of running Hadoop away from the users in a managed service. But still, that comes at a significant cost. You just generally have to assume that you spend roughly 20 to 25% more on these managed instances of Hadoop than on the similar instances for other cluster technology, like EC2, etc. The good thing about that, it also makes it a bit easier to run on managed services, because essentially HDFS, the old distributed file system, is basically the native to Hadoop, has been largely replaced with object stores such as S3, blobs, and buckets. So it makes it much easier to distribute the data. But generally, it's still difficult and costly to run EMR. So generally, the deployment target is using a standing cluster, or when available on your public cloud platform, which is spin up an on-demand cluster and just run step functions. In AWS, you can do that quite easily by saying, okay, this is my job, I'm going to deploy it. You start an EMR cluster, it spins up the cluster, deploys the job, runs the job, and when the job is done, results are collected and the cluster is destroyed until you basically need to run the next batch job. This has some pros, but also a lot of cons. So the pros of running a Spark in that infrastructure is that it's been around for a really, really long time. So it's very mature, very reliable, and there's a lot of resources that describe how to do that. You have not only the ability to run Spark on Hadoop, but you also have lots of integrated tools such as Hive, which is essentially a SQL implementation of distributed SQL implementation on top of Hadoop. You can use notebooks, which are very popular in the data science crowd, etc. You also have excellent managed services from your Google Cloud providers. Generally, that's very well bundled and well understood by the three of them, the three big ones, AWS, Google, and Microsoft. So it's actually fairly easy to set up. Issue, obviously, is that it's costly and probably not very efficient either, because every, let's say, worker node, Spark worker node runs on a VM and not on a container. So you can't leverage the advantages of container technologies in a Hadoop cluster. Ramping up those clusters is also very slow. It takes roughly 8 minutes for an EMR cluster to start up, so before you actually even deploy and run your job. And it's also very siloed. So again, the major drawback, especially for this crowd and this webinar, is obviously how do you integrate this pretty much alien technology in otherwise a microservice or VM landscape. It is a technology that is not used anywhere else but in data platforming. So there is also the additional operating overhead of having to integrate that into your landscape. And specifically to Spark, you can't just run any version of Spark that you want. It's always tied to the environment and the Spark version that's provisioned and bundled with the EMR and Hadoop cluster that you're running. So again, if we remember, Spark was initially designed to run as an application framework on multiple clusters. Well, like for Mesos, its own standalone environment in Hadoop, but also for the last couple of years, Kubernetes. And it's now fully GA, so it's generally well tested. It can be used in production. And it gives us the ability to run the jobs in two different modes. One is essentially the bundled version, which basically uses Spark tooling. Basically says, okay, I'm going to stage the job for you and run it on the cluster. And the other one is using a Spark operator, which is really, really flexible because it also leverages the enormous benefits of Kubernetes. So if we look at the easy way that's bundled, Spark Submit, it's relatively simple, but it can be used by anyone because it's just running a script. It packages the application, executes the driver, which is like the main stage of a Spark job that does all the planning and plugs in all the bits and pieces together, and then basically runs an executor pod on the cluster. Drawback is obviously because it's very simple, it will just assume the default permissions and node types that are available to a cluster. You can't specify anything. But it's bundled with Spark, it works out of the box, super easy. Right? The other option is to use the operator. The Spark operator is really cool because it uses Kubernetes custom resources. It's funny enough not something that came from the Spark project itself, but it's something that Google started. It gives you basically a declarative approach to application specs and management. You can basically configure the instance and node types that you want to use, config maps, volumes, pod affinity, and all of that. And most importantly, in terms of security, it gives us the ability also to configure instance profile especially on Google Cloud with service accounts. So essentially, you can say, instead of running on the defaults of a cluster, you can specifically say, look, this job will want to write to an S3 bucket, will want to talk to Kinesis, or will want to write to a JDBC RDS instance in AWS. Most of you work with AWS, so that's why you'll forgive me if I use most of those references. But it gives you the ability to actually configure those profiles specifically and tie down security aspects of the Spark job to the specific instance profile that runs with that service account. And that also gives you the ability to customize the versions that you're running against. So in contrast to, let's say, Hadoop deployments, where you're basically tied to the version that's bundled with the cluster down to the JDK version, you can actually basically do pretty much whatever you want as long as you can provision an image for the operator. So it is a very, very flexible way to run Spark on Kubernetes using all the tools and the wonderful things that Kubernetes can give us. So the big advantage is that you essentially run Spark, and therefore you basically merge all that data engineering stuff and into your normal ecosystem and application landscape, which is a big benefit, especially, let's say, for let's say, platform engineering teams that have to deal with the demands of, let's say, a normal, quote unquote, normal, a regular software development teams with running microservices, as well as data engineering teams. You can also you have great benefits in testing your Spark applications just using containers. Before that, with Hadoop, it was much more difficult. You can run different versions of Spark with completely different security contexts and permissions. You can fine-tune all of that, and it's much more portable also across public clouds. And that's also a big advantage specifically, which is obviously also one of the benefits of using Kubernetes. If you basically have to deploy your Spark environment in, let's say, in AWS and Azure, well, you could just do that with the same configuration. If you just think, I get back to Hadoop, let's say the runtime behavior and the deployment artifacts and the deployment machinery is heavily tied to the actual cloud provider that you're using, especially if you're using stuff like Terraform. You can't port that across different clouds because the environments are completely different. And lastly, your CFO will also be quite happy because it is significantly cheaper to run the same Spark applications on Kubernetes, roughly 20% savings on an AWS deployment. And beyond that, it's also much faster because you also save ramp-up times in deploying your applications on clusters. There's obviously still a bit of work to be done. Not everything is available. There's like some artifacts and tools around Spark that need to be configured specifically. We've done that work at Hivemind because it's actually quite useful. And some aspects of dynamic allocation, specifically in job planning and resources, are not as effective, let's say, especially if there's variance on Kubernetes, because it's not as mature as it is on Yarn. Well, there's obviously also, let's say, roughly 10 years of development difference between, let's say, the implementation of Spark on Hadoop versus the one for Kubernetes. But in a nutshell, it's really, really about time to say goodbye to Hadoop and Yarn, do away with all of that, and run all your data applications on Kubernetes. Thank you very much.
Thank you, Erik. Let me reappear. That was really interesting. Fantastic. Well, so we have another 10-15 minutes for questions. So
yeah,
as I said, feel free to drop your questions either in the chat or using the Q&A, whatever you guys prefer. And we can wait a couple of minutes if there are any questions. Don't be shy, guys.
Absolutely. Go.
All right. So we have one here by another Erik. How does Spark on Kubernetes do away with Hadoop? I thought Hadoop was about storage. So, well, what to use instead? I can understand Yarn because Yarn is a schedule just like Kubernetes.
Yeah, exactly. So yeah, that's a very good question because Hadoop is specifically a family of different things, right? And the main components of Hadoop are HDFS, so Hadoop Distributed File System, and Yarn, which is a job scheduler. So going back to my history slides, like GFS, which was the Google file system, and MapReduce were the basic ideas, the inception that gave birth to those two tools, Yarn and HDFS. And funny enough, HDFS is actually not used that much anymore, actually very rarely used, because we have very efficient object stores that do exactly the same thing, notably S3, Azure Blobs, and Google Buckets. And funnily enough, those three actually implement HDFS as an API. So can you basically use HDFS in conjunction with the driver to execute HDFS commands on S3, Google Blob, and so on. So the storage stuff is actually solved. It's actually been solved much more recently. Not recently, it's been solved for a while now, even though Hadoop is still being used, right?
Just a quick one. So is Hadoop a primitive ancestor of Kubernetes, I guess, in line with the history lesson?
Yes, indeed, because let's say what Hadoop, specifically Yarn, did was introduce a concept of containers, right? Of sort of containers, right? So the instances, because Yarn nodes have execution slots, right? Where you can basically put in a job that basically communicates with Yarn. So it's very similar, right? And in fact, the newest version of Yarn, 3.0, supports Docker containers. So you can actually deploy Docker containers to Yarn and run Docker containers within Yarn. Nobody does that because Kubernetes is so popular, but let's say the Yarn folks were saying, okay, wait a minute, Docker is around, we want to do the same thing. It's actually not that difficult. We just have to basically provide a runtime that runs Docker within Yarn. Yeah.
Interesting. I didn't know that. All right, lots of questions. So have you used Dataproc and how do you find it? How do you find it compares to Spark on Kubernetes?
Now, I'm not, as I said, I'm pretty much an AWS guy, so I haven't used that much. But if I'm not mistaken, and please don't shoot me if I'm wrong, Dataproc is essentially pretty much an envelope around one of the let's say the big distribution of Hadoop. So it basically implements Hadoop for Google, and if I'm not mistaken, it should be Hortonworks that they just picked and implemented. And I think Azure, Microsoft did the same for HDN sites.
Dataproc is same as using EMR or Hadoop.
Yeah, exactly.
That's it. Yeah.
That's correct.
What is the plan for Spark and Kubernetes dynamic allocation, and what is the current situation?
So it's actually there's a bit of intricate problems with dynamic allocations. So generally, it's relatively static. So when the job starts planning the stages, it will request X instances for the job. And what Kubernetes does is basically allocates those instances and locks them for the time of the entire execution of the job, right? And it doesn't free them up. So it uses a lot more resources than it would in Yarn, because in Yarn, basically every stage has its own dynamic allocation run, and will basically then just request that many containers from the cluster. And then once that stage is done, it basically frees them up. So that's the one bit that they're still working on, to figure out how to free up the resources after each stage, rather than blocking them for the entire duration of the job. So that's why it's using dynamic allocation is just fine in Spark, but it costs more instances and more runtime.
All right. Any insight on the cost performance difference between running Spark jobs on EKS versus Databricks?
Okay. Well, Databricks, I am not that familiar with Databricks. currently, because like last time I used it was pretty much Hadoop, so it was very it was running on Hadoop, on their own version and flavor of Hadoop. I don't know what they're doing right now, but generally it was pretty much on par with EMR. So just running stuff on Databricks, on the Databricks cloud, was very similar to running the same jobs in EMR. EKS specifically is cheaper, right? And because we don't have that overhead of like running in entire instances. The instances are obviously cheaper, and you can slice down the individual tasks to smaller units and run them parallel on one machine. So generally, it's more efficient.
Got it. So Dan is asking, how resilient is Spark on Kubernetes to instability such as node failures?
Well, yeah, so Spark is actually quite resilient, and that's actually inherent to Spark in pretty much all cluster containers, cluster technologies it uses. So generally, Spark has a concept of retries and attempts, right? And it's actually relatively quite clever, because it will basically start to run and plan and distribute all the different partitions of a stage to all the available nodes. And when some of them fail for basically memory problems, it will then try to spill stuff to disk or reallocate the stage to instances that have more, that are not running other tasks in parallel. So there's quite a few clever mechanisms to basically do retries and reattempts. Doesn't mean that it never fails, and of course, especially if let's say the available physical memory of the instance is too small to fit the partition, the job will definitely always fail, regardless of how often it attempts. But other than that, it's actually fairly resilient, and you can actually rely quite on Spark's mechanism and retry mechanism. Quite, they're quite clever. Yeah.
Interesting. Amit, first of all, very nice presentation.
Thank you.
My question is more to the maturity. So specifically to around some features like Spark UI and dynamic allocations. Are there companies using these in production, or is there more pain in adopting it in prod in terms of maintenance?
No, I think that generally the fact that it's now GA, and it's been GA since Spark 2.3, and we're now at 3.1, is absolutely it's reliable and it's good to use. We use it massively in all our projects in production. The only, I'd say there's a bit of difference in comfort, right? Because running in it's running everything in Hadoop is basically the equivalent of spending your vacation in an all-inclusive club. There's a bar, there's a restaurant, there's everything is available, rather than having to go to that boutique nice hotel and then having to find a restaurant and a bar on your own, right? So that's maybe the comparison. But generally, running like Spark UI and Spark History Server along your job is fairly straightforward, and we've actually provided, like for our clients, we basically provide that out of the box, so we can just deploy that along with the job.
I like that analogy. Hi, Erik. We use Spark Hadoop with local SSDs for HDFS in the Hadoop cluster. What option do we have to replace the ultra-fast local HDFS storage if moving to Kubernetes?
Well, of course, you can always basically, it's always a bit of a question of why you're using HDFS and SSDs locally, and how your jobs are designed and how often they flush to disk, right? It's probably also very specific to that use case. You can obviously plug in the same thing into your Kubernetes cluster, but that might be a bit weird. Generally, I think that predominantly in our use cases, especially in Amazon, we basically rely on S3 and configure that, and that works quite well out of the box. But indeed, if you're really looking at fast access and you need that efficient read and write facility, and HDFS is the way to go, then that's probably a more difficult one, because there is no equivalent in Kubernetes for HDFS.
All right. Omid, I believe at reInvent, there were some talks that claimed EMR uses an optimized Spark runtime, and they were claiming that it's cheaper, more performant than running Spark native on EKS. Do you have any insight or opinion on this?
we haven't made that observation, honestly. I mean, there's one bit that's actually quite relevant, and that plays a small role, specifically when using Spark on EMR with S3. Because let's say there's this concept of data locality. So Amazon is relatively clever in allocating and resources and making sure that the access between the S3 storage and the EMR cluster is relatively quick. There's a bit of a performance difference, but we haven't actually measured or made it. I haven't actually noticed anything significant that would justify the benefits. The trade-off is just not there. But that's our observation. We don't have any hard evidence to point in one or the other direction.
Cool. That was it. Any more questions? I was just checking the YouTube chat, but no questions there. Let's see. Does dynamically scaling in and out work with Kubernetes? Use case like serverless EMR or glue?
Yeah, those are basically different approaches, right? So
Right.
in Kubernetes, as I said, with dynamic allocation, there's still some work to be done. So what you can't really do is use dynamic allocation on a Fargate cluster, right? Doesn't really work. And on top of that, with dynamic allocation, you basically have the issue that it will reserve those nodes for the duration of the entire job. If you can live with that, that's fine. But I don't think that you can, it's otherwise not that comparable with EMR serverless. EMR serverless has its merits, where if it says you have this one-off job, you want to run it, you don't want to be bothered. That's absolutely, let's say, a legitimate choice, right? I think that the case for running a Spark on Kubernetes specifically is for those companies that already have a Kubernetes cluster and just want to basically reduce the operational impact and save money at the same time. So because if you have already on the Kubernetes cluster, you're already running some workloads, and you're basically geared towards operating your Kubernetes cluster, that's generally a good idea to run Spark on Kubernetes as well.
Is high availability support on Kubernetes? I think you might have answered that already.
Yeah.
Will you recommend Kubernetes for streaming jobs?
Yes, you can also, we do that quite a lot. So we basically use Spark Streaming on Kubernetes. It's really quite brilliant, actually. Yeah.
Nice. All right. I think we can wrap it up because we're on time as well. Thank you, Erik. This is really interesting. We still have a lot of people hanging around and asking questions, so that's awesome. And thank you, everybody, for the questions. Do you want to do any plug, Erik, before I do mine?
Excuse me?
Do you want to do any plug? Send people anywhere?
I don't quite understand. Sorry, no.
No? Okay, that's good. So I'll plug Platform Con. So for everybody, we've recently launched the updated set of Platform Con. New thank Azadiva. New lineup. It's quite exciting. We recently opened the CFP and we already have, I think, like 50, 60 requests for talks. So it's pretty cool. So go sign up if you haven't yet. It's free. And if you want to submit a talk, also submit a talk. Erik, you're welcome to do the same, of course. So thank you so much for the time. Thank you, everybody. Go check out